Much like Friday, our notes today are going to be a bit of a mashup of things from 10.2 and 10.3. Because there was something that showed up in both of those sections that we never really discussed. And you may have noticed it on those book assignments that there was some sort of weird notational thing going on that you'd really probably never seen before. So today, a mixture of 10.2 and 10.3, we're talking about summation notation, also known as sigma notation. So you may or may not have noticed that as you were looking at the sections, there were some problems that had something like this written on them. This is called summation or sigma notation because this thing right here is the capital letter sigma. It's a Greek letter. You've seen a lowercase letter for sigma before. We will see the lowercase version of sigma again in the future. You generally see the lowercase a lot more often because the lowercase shows up in statistics. It's the little O that looks like it's got a hat coming off of it. That is lowercase sigma. It's used for standard deviation. And it will come up again when we get to our stats unit. Capital sigma tells us that we are going to add up something. And if it's telling us that we're going to add something up, it is telling us, in terms of sequences and series, that we are talking about a series. Sigma notation is used for series. Now, what sigma notation actually is telling us is it's telling us that this right here, this 2K, is the expression, kind of like the equation. The only difference is it doesn't have an equal sign. This expression is going to be used repeatedly for K values that start at 3. So this is the first thing or the first input that goes into the variable. So we're going to use the expression 2K, and we're going to plug in 3, and we're going to continue to plug in numbers up until we get to the number 12. This is the last number we input. So for this particular problem, that means that this is equal to 2 times 3, because that's the first thing we plug in. That's the end of the expression, so now we do our plus sign. And what we do is we increase the value of K by 1 up until we get to this number up top. So the next number I plug in is 4. That's the full expression, so I do plus sign. So then the next number I plug in is 5. Then I do my plus sign, and I keep doing this up until the last number I plug in is 12. That's how we interpret sigma notation. That's what summation notation is telling us to do. To just keep plugging in numbers, starting at this one, ending at this one, and then to go through and actually do the adding of it up. Now, once we have that interpretation, how to actually approach the problem is no different than we've already been approaching series. Once we know how to interpret this, we're still going to ask ourselves, is it arithmetic or geometric? In this case, it is arithmetic, but I'm talking in general. The way you can tell if it's arithmetic or geometric is based on what the expression looks like. If the expression looks linear, it's arithmetic. If it looks exponential, it is geometric. Now, to help you out with if it looks linear or if it looks exponential, arithmetic ones look arithmetic. Geometric ones look geometric. If I give you something like a sub n equals 4 times 5 to the power of n minus 1, is that an arithmetic or a geometric equation? It's geometric. The variable's in the exponent. That is what summation notation ones will look like as well. If I give you something like a sub n equals 5n plus 4, that's what arithmetic expressions look like. So, when it comes to working with this sigma notation, we are going to be working with our series formulas. And we put together this sheet in our notes that kind of started to gather together our formulas last week. Throughout each of these formulas, there are specific things that we need. So one of the key things you have to be able to do is to find the important variables. Now, the different variables that go into our equations. For the series, it starts with S sub n. But if I give you sigma notation, that's always going to be what you're looking for in the grand scheme of things. There's not some special way to find it. That is the last thing you find. You have to find things like a sub 1. A sub 1 is the first term in a sequence or a series. In this case, for this one, that first one was that 2 times 3. In other words, 6. Where did the 2 times 3 come from? Why did I start it as 2 times 3 and then 2 times 4, 2 times 5? How did I know to start here? I pointed it out earlier. It's this getting plugged into this expression. So to find a sub 1, plug in the number below the sigma into the expression. Now they're always going to tell you variable equals on that number below, and that variable is also trying to tell you which variable they're using, because in all technicality, summation notation can be multivariable. We're not going to have a multivariable. We're going to have this letter matches that letter. 90% of the time it's K. They can use other letters if they really want. I is also a very common one. K and I most of the time take up what most textbooks do. But it could be multivariable technically in here. So the reason they put the variable down here is to tell you which variable to plug it into. Okay, a sub n is another thing that you might want to find. A sub n is the nth term in all technicality, but when you're adding up n terms, it's the last term. And the last term that I had was this 2 times 12. Where'd that come from? The final input getting plugged in. So you plug in the number above the sigma into the expression to get a sub n. N tends to actually be the one that trips people up the most. Not because it's particularly challenging, but because it's not always the most intuitive thing to find. In this expression, I plugged in 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. I plugged in a total of 10 numbers. So for this particular expression, n is 10. And you could have gone through and counted that out just like I did to figure out what n is. And that works beautifully if the numbers are relatively close together. 3 to 12 is not a terrible count. 4 to 500, less friendly. The reason that this tends to not be intuitive is because most of the time what people like to do is they like to say subtract those two numbers. Because if I'm plugging in the numbers between 12 and 3, we subtract them, we get 9. You have to add 1 back in, because when you are trying to figure out how many numbers you have between two digits, by simply subtracting them, essentially if I had the numbers 1 through 12 listed out, and I'm saying, well, I'm only adding up the numbers between 12 and 3, and I take 12 and I subtract 3. What I'm actually taking away is the first 3. But didn't we want 3 included in that? So you always subtract and then add 1 back in, because you always will have subtracted 1 too many. So that is how we find n. N is always the top number. Minus the bottom number. Plus 1. And people tend to forget that plus 1. It's not a hard calculation. A little bit of subtraction, a little bit of adding, nothing too terrible, but you do need to remember to add that 1 on there. Now, the other 2 variables that you might need are either R or D, depending on if it's arithmetic or geometric. If it is geometric, that's where R comes in. Each of these sigma notation problems will always have the expression looking like that of an arithmetic sequence or a geometric sequence. So they're always going to look like one of these 2 setups, where they actually look like the sequence formula. R, in the geometric sequence formula, is the base of the exponent. D, which shows up for the arithmetic sequences, that constant or common difference is the slope of the expression. It's the coefficient of the variable. Now, in all technicality, this summation notation is not specific to arithmetic and geometric theories. But for this class, for this unit, we're going to focus in on arithmetic and geometric. So we're going to focus in on doing things this way. Now, once you've found the variables necessary, which you don't always need all of these variables, I hope that's obvious. If it's arithmetic, you don't need R. If it's geometric, you don't need D. But once you find these variables from here, it's just recognizing it's a series, and therefore I plug into the series formula. So, you're going to be asked to find the following. And then they'll give you an expression. Now, in all technicality, if it is arithmetic especially, you're going to see either brackets or parentheses around the expression. And you have to have that, because if you don't actually have that, if this was just 2k without the plus 1, or sorry, without the parentheses around the plus 1, then the sigma notation actually would end at the 2k, and the plus 1 would just tell you once you found the sum of the series that had 2k, then at the very end of that, it would tell you to add 1 to it once. By having the plus 1 in the parentheses in the bracket, it's being interpreted that that is all a part of actually finding our sum of our series. So, to approach these problems, you're going to approach them the exact same way that we've been approaching all of these problems. We're going to determine, is it arithmetic or is it geometric? Is it a sequence or is it a series? That one should be obvious. The moment you see sigma, you should be thinking series. But is it arithmetic or geometric? Does this look like a linear expression or like an exponential expression? Looks linear, therefore it is. This is an arithmetic series. Arithmetic series have two different formulas. S sub n equals n over 2, a sub 1 plus a sub n, or S sub n equals n over 2, 2a sub 1 plus n minus 1 times d. Which one you use is a personal preference if you can find the variables for both of them. If you can't find the variables for both of them, then you use whichever one you can find the variables for. They both require n. Can we find n? To find n, the thing that causes the most issues with sigma notation. Top number minus bottom number plus 1. In this case, that is what minus what plus 1? 15 minus 4 plus 1. 15 minus 4 is 11 plus 1 is 12. We're adding up 12 numbers. When in doubt, could we count them? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 12. Okay, both of them require a sub 1. A sub 1 is found by plugging in the number below sigma into the expression. So I'm plugging in the number 4 into 2k plus 1. 2 times 4 plus 1. 9. from here, the top formula requires a sub n, the bottom formula requires d. Which formula would you rather use? I prefer this one. Some people would prefer this one. D is easier to find, which is why some people prefer the bottom one. What is D? 2. It's the coefficient of the variable. A sub n's a little harder to find, but to find a sub n, you just plug in 15 into the expression. Do I have to find both of these? No. But this is easier to find than this. So if you prefer to find that and use this formula, go for it. If you'd prefer to find this and use that formula, go for it. I just prefer the first formula, so I take the extra work of plugging this in. S sub n equals 12 over 2. I'm going to use the top formula, so a sub 1 plus a sub n. 6 times 40. 240. Now, just as a heads up, because of the fact that so much of what we do nowadays is in a computer, and computers have some limitations on how they write things out, there's one slightly modified way that you'll see this notation pop up. And it's considered a condensed way. And what they'll do is they'll have the sigma symbol. They won't have numbers above it and below it. Instead, they'll have numbers here and here before they give you the expression. They're doing the same thing. It is no different. It's a condensed version of sigma. It makes the sigma piece of the equation smaller because that's the piece that gets bigger and takes up more room when typing it out. Jada, is this arithmetic or geometric? Yes. Brandon, is it a sequence or a series?
It's a series.
How do you know it's a series?
Because it's in summation notation.
Because it's in summation notation. The moment you see sigma, it's series. It is in the name. It says summation notation, but if you forget the name of it. Okay, so geometric series. Got a couple of different formulas I can use, both of which require a sub 1. Lainey, how can I find a sub 1?
You plug the k equals into the k spot where in the exponent.
You plug in that k equals number into the expression. Four times negative 2 to the power of 2. Okay, negative 2 to the power of 2 is 4. 4 times 4 is 16. both of those equations require r. Bryn, how do I find r?
I don't know. Oh, -2.
Base of the exponents, -2. One of those equations requires n, the other one requires a sub n. We're going to find them both for the practice of our notes. For the homework, you don't have to find them both every single time. Logan, how do I find n?
Top number minus bottom number plus 1, so 10 minus 3 plus 1.
10 minus 3 is 7, plus 1 is 8. Lindsay, how do I find a sub n? Plug the top number into the expression. So 4 times -2 to the power of 10 minus 1. 4 times -2 to the power of 9. Negative 2048. Lauren, which of these two equations would you rather use? Okay, sure. And what would it look like if I use it?
16 minus 1. Oh, sorry, 1 minus -2 to the power of 8 divided by 1 minus -2.
Good. Addie, where does this need parentheses? Is there anywhere else? Anytime r is negative or a fraction, it needs parentheses before you put an exponent on it. Any more? What do you get?
I got -1,360.
So did I. This next problem uses n instead of k. That changes nothing about what we do. Absolutely nothing. Try out the following two problems. When you have them done, have me look it over.